My name's Stephen Haunts, and welcome to my talk on .NET Data Security, Hope is Not a Strategy. So I'm the head of development for a company in the UK called Buy & Butler. We're an online buying concierge service for buying motor vehicles, and we also have a second product which is to do with insurance claims management, which is why a lot of the security concepts we're talking about today are quite important, because it's all about protecting people's information. I'm also an instructor for a company called Pluralsight. So has anyone heard of Pluralsight, or does anyone use it here? Oh, great, quite a few of you, cool. So I've been working with them for about 3 years now, and I've done 8 courses with them. So we're going to cover quite a lot of information in this hour, but if you do want to take a more considered approach to the subject, I do have a course on Pluralsight called Practical Cryptography in .NET. It goes into what we're talking about today, but in a lot more detail. And also have a second course, which you might find interesting, which is taking some of the concepts we discussed today around key management and applying them to the Azure Key Vault. Also, all the source code for what we're talking about today and for the Pluralsight course is available on GitHub. So you feel free to go and take that code and just use it in your own solutions if you wish to. And also, all of these slides are available on GitHub as well, at that address there. I'll show this slide again at the end. So if you want to use the slides to refer back to at a later date, you can. So why am I doing this talk? So I believe that as developers, it is our responsibility to our organizations to protect our company's data. So there's a lot of power in your hands, the people who are building the solutions. But generally, a lot of companies tend to take a very blasé approach to security, and they tend to have this attitude that, you know, we're too small to be attacked. No one's going to try and steal our data. They're just going to go for the big companies. But that's completely wrong. Nobody's too small to be a target when it comes to security, which is why this talk is called Hope is Not a Strategy. You know, hoping that you don't get hacked because your company is small or you don't think that your data will be that valuable to attackers is a completely wrong strategy to take. You have to take security very seriously in this day and age. So when I was writing this talk, I found this book here, which kind of sums up how a lot of project managers run their projects. Has anyone kind of had a situation like this where they work, where security is just pushed towards the end of the product or project and then left? Yeah, this happened to me a few times. Okay, so what this talk isn't, so it's not a deep mathematical exploration of encryption algorithms, so we wouldn't have a chance to do that in an hour. And you know, it's nearly lunchtime. I'm sure nobody wants to do any complex maths at this time of day. The talk's also not about cryptanalysis. So cryptanalysis is about, you know, the art and science of breaking codes, the sort of things that our governments love to do to us every day. So the talk's not about that either. But what the talk is about, it's about people like you and me who work in teams for everyday companies building solutions. So this is about exploring some of the tools that are available to you and how to apply them. So a lot of what we're talking about today applies to the .NET framework, so most commonly server-side programming. So if you do web APIs, WCF services, all that sort of thing, then this is very relevant to you. Also, if you still do client-side applications in WinForms or WPF, then a lot of what we're talking about here is quite relevant. But although we're focusing on Microsoft technologies, actually the principles of what we're discussing is kind of platform agnostic. So whether you're a PHP developer, Python, Ruby, Swift, everything we're discussing today is completely relevant. It's just they're different APIs. So quick show of hands, who's .NET developers in the room? Okay, anyone use any other language? Okay, so those of you who use other languages, majority of what we're talking about is still relevant. It's just the APIs will be slightly different in your chosen language. So what we're going to cover, so we're going to go through all of the primitives that are available to us as software developers. So we're going to start off by looking at random numbers. Then we're going to look at hashing algorithms and authenticated hashing. Then we're going to talk about secure password storage. Then we're going to talk about symmetric encryption, then asymmetric encryption, and then digital signatures. But then once we've covered all of those primitives, we're going to talk about how you can use them all together to form what is called hybrid encryption. And this is where you get a lot of the value from using these primitives. So first of all, what is cryptography? So cryptography is all about protecting information so that people can't read it. And generally, this is done using encryption, and you use encryption keys to encrypt that data. And this produces what is known as ciphertext. So that's the result of an encryption operation, which nobody should be able to read. And then, as we said earlier, cryptanalysis is all about people trying to break the encryption algorithms to recover your original text or your original data. But there's more to cryptography than just confidentiality. There's 4 main pillars around cryptography. So the first one is confidentiality, as we've just discussed. Then there's integrity, so that's using cryptography to prove that data hasn't been tampered with or corrupted. Then there's authentication, which is about proving that you are the person who sent that information or that message. And then there's non-repudiation, which is about not being able to deny that you sent a message. So if you think of it in terms of if you're signing a contract to a lawyer's or solicitors, sometimes you have a witness present. Well, that witness is there so that you can't deny that you signed that contract. And it's the same theory in cryptography with non-repudiation. So cryptography is everywhere. You cannot literally do anything during the day without running into cryptography. You just can't see it most of the time. So every time you use the internet or do online shopping, you're going over a secured link, but that's all cryptographically secured. When you use the bank machines and put your card in and your PIN number, there's a cryptographic handshake going across the network to the bank. Your mobile phones are all generally encrypted these days. And remember the FBI trying to get into the iPhone of the San Bernardino killers last year. The thing that stopped them was because of the encryption on the phone, and Apple sort of stood their ground and refused to unlock the phone, which I think is a good thing. But there's also using things like cryptocurrency, so things like Bitcoin, Litecoin, and all the blockchain sort of related technologies that are coming out at the moment. And another area where it's used in some countries is electronic voting systems. Okay, so let's look at our first set of primitives. So we're going to talk about random numbers. So random numbers are pivotal to everything we do in cryptography. So without a good set of random numbers, then we can't do effective security. So a random number, in the context of what we're talking about, is a very, very long string of digits. Typically 32 bytes in size, which is 256 bits, is a common length. So for those of you who use .NET Framework, one thing you don't want to do is use system.random. So if you're trying to generate lottery numbers or simulate a dice throw, system.random's fine. But for generating encryption keys and strong random numbers, system.random is not what you want to use. So what you do want to use is a decent random number generator. So in .NET, that is called the RNG crypto service provider. And what you'll see throughout this entire talk is a lot of these classes and objects have really silly names, which is why a lot of people completely skip over them when they read the documentation. So everything we're talking about today lives in the system.security.cryptography namespace. So if we look at sort of how we use this, it's very easy to use. Most of what we're talking about today is very easy to use. It's just kind of getting the principles in your mind. So to use this one, so we generate the RNG crypto service provider class instance. We pre-initialize an array. So in this case, it could be, say, 32 bytes in length, a byte array. And then on your random number generator, you just call getBytes, pass in that array, and it gets filled full of random gibberish. And that's kind of the basis of everything that we're going to use going forward. So when we need to generate encryption keys, this is the method we're going to use. So if we move on to our next primitive, and that's called hashing. So a good way of thinking of data hashing is it's kind of like a fingerprint for a piece of data. So if you have, say, a PDF document and you generate a hash code for it, you get like a long number or a long string at the end of it, and that's kind of a unique identifier for that piece of data. And there's 4 principles that hashing needs to adhere to. So a hash needs to be easy to compute. So you have a piece of data, run it through a hashing function, and you get a hash code at the end of it. So it has to be easy to use. It needs to be infeasible to generate a specific hash. So you can't have a target hash and try and work out what data you need to generate that hash. That should be impossible to do. And it should be infeasible to modify your original message without completely changing the hash. So if you have a PDF document and you generate a hash code, if you change one bit, literally one bit in that document, the entire hash code should be completely different. Not slightly different, but completely different. And it should also be infeasible to find 2 identical hashes. So you shouldn't be able to have 2 documents that generate the same hash. That's called a hash collision, and that's bad. So one good way of thinking about hashing is it's kind of like encryption, but it's one way. So you have a piece of data, you run it through this hashing function, you get this long piece of gibberish out the other end, but you can't go back the other way. Whereas encryption is a 2-way operation. You have some data, you encrypt it, and you can then decrypt it back to the original data. So when we look back at the history of hashing, one of the most common ones that was out there was one called MD5. And this produces a 16-byte hash value. So if you hash a document, for example, you'll get a 16-byte value back. And this was designed back in 1991 by Ron Rivest. But in '96, a load of researchers found that there was a collision resistance vulnerability with it. So it's actually possible to generate the same hash from multiple messages. You'll still commonly find this in the wild. So if you're working with a lot of legacy systems, you'll probably still have to work with hash codes or MD5 hash codes. But if you're building a new system, then generally you want to stay clear of MD5. So moving on from that, then we have the secure hash family called SHA. And there's various different variants of it. So we have SHA-1, which generates a hash code which is 160 bits in length. And then we have SHA-2, which produces 256 and 512-bit hash codes. Both SHA-1 and SHA-2 were designed through competitions that are run by the National Security Agency in the US. So naturally, this gets a few people nervous that someone like the NSA has control over designing algorithms like this, even though the algorithms are publicly sort of verified by researchers and organizations. But to get around this nervousness, there was another competition that was ran back in 2012 to find what was called SHA-3. And the idea is that this is a new hashing algorithm that is designed without the involvement of the NSA. And the winner of that competition was a cipher called the Kekak, I think that's how you pronounce it, cipher. But SHA-3 doesn't currently exist in a .NET framework, but I'd expect it sort of reasonably soon. So generating a hash of a piece of data is very easy to do. So we have a static object called SHA-256, and you call .create. And then you pass in a byte array of your data that you want to hash, and then you get a byte array back out the other end, which is your hash code. So all the APIs we're looking at today all work on byte arrays. So if you need to, say, convert a string or encrypt a string, then you'll need to turn it into a byte array first. So the next type of hashing is called authenticated hashing, and it's very similar to what we've just discussed. You have a message in, and you get hash code out. But with authenticated hashing, you can also pass in a key. So literally all a key is it's 32 bytes of random data, which is generated with that random function we looked at earlier. And the purpose of this is that once you've generated a hash code, for someone else to generate the same hash code from that data, they need to have that key. So it's a way of proving that you as the person who originally hashed that data, because you have to provide the same key. So these are, so they're called HMACs. They're typically called message authentication codes, and they're used to verify both the integrity and the authentication of a piece of data. And what we mean by integrity is if I have a PDF document and I generate a hash code of it, and I send you that document, if that document's been modified in any way, when you recalculate the hash will be different. But if the hashes are the same, then you know it's the original document. But then adding the concept of authentication just means that you can make sure you can restrict who can generate that same hash code with a key. So generating a hashmark is just as easy as generating a normal hash. So we have a class called HMAC SHA-256, which we create an instance of. We pass in the byte array, which is our key, so 32 bytes. And then we call compute hash, passing in the data we want to generate the hash code for, and we get a byte array back out the other end, which is our hash code. Now, hashing has very commonly been used for storing passwords in databases. So does anyone work on or has worked on systems where you generated a hash code to store a password, like an MD5 or a SHA-256? So we've all done it. And generally, this has been fine. But the problem with that is a hashed password is actually very easy to crack. So the way an attacker will try and do it is through what's called a brute force attack. And they do that using what's called a rainbow table or a dictionary attack. And what a rainbow table is it's literally just a database of hash codes and different password combinations. And these dictionaries run into multiple gigabytes in size, and you can just freely go download them off the internet. And they even do clever things like changing the vowels into numbers and putting exclamation marks at the end. So all those things that people typically do to secure their passwords, you're not really securing them at all. And the main problem with this is that with modern GPUs, graphics processing units in your computer, you can now test billions of hash code combinations per second. So actually trying to brute force attack a password that's been stolen is actually very easy to do. And you can download programs like Hashcat, which is freely downloadable off the internet, and that will do that for you. So if you've got a very powerful graphics processor in your machine, then Hashcat will use the processing power of that card to start cracking hashes for you. So an example here, and there's lots of these on the internet, this is a website called crackstation.net. So we have a hash code, which has been pasted into the top there. That's what one looks like. And then once you typed in the captcha, you just say crack hashes, and it's worked out that it's a SHA-256 hash, and it's recovered the password, which in this case is secret 69. So that's kind of an example of how a brute force operation works, but that's happening billions of times a second. So one way people try to combat this is by doing what's called salted hashing. And this is where you get your password and you append what's called a salt onto the end of it. And that literally is 32 bytes of random data, which is just added onto the password, and then it's hashed. But to do this, you need to store that salt somewhere so that you can actually recover the password later on. So if you're working with a system that does that, then ideally you don't really want to store the salts alongside the password because you're just making the attacker's job very easy. That's one way that's commonly been used to store passwords. But again, it's not that foolproof. So the better way to do it is to use what is known as a password-based key derivation function, or as it's a snappier title, PBKDF2. And whilst that sounds complicated, it's really not. So what it is it's a normal hashing function. So we pass in the password and we pass in a salt as well, but we also pass in this third parameter, which is called number of iterations. And what that does is it multiple hashes that password. And the reason it does that is you want to algorithmically slow down the hashing process. So whereas before, with a normal hash, you can calculate billions of these per second, if you have a high iteration count, you might reduce that down to, say, 5 a second or 2 a second. So whilst they're still doing the same hashing operation, it's much slower. And really what you want is the attackers just to get bored and then move on and find another target. So again, it's very easy to use. We've got a very snappily titled class here called RFC2898 derived bytes. A lot of people miss it in the API documentation because it's not very obvious what it is, unless you're familiar with internet standard codes. But what we do is we create an instance of that class. We pass in our data to be hashed, again a byte array. We pass in our salt, again which is a byte array, and a number of iterations. And then we call get bytes, and we pass in 20. So the reason we're passing in 20 is because under the covers in the implementation, it uses SHA-1. And SHA-1 gives you a 20 byte hash code back. So back when I originally wrote this talk, I did some timing tests just to look at how long it takes to run these operations. So if we do 100 iterations, it took 2 milliseconds to encode a password. And then I tried it with 1,000, and it took 16 milliseconds. And I tried that all the way up to 500,000 iterations, which took just over 7 seconds to calculate the password. And obviously, if you've got a website and you make your user wait 7 seconds, then they're probably not going to be very happy. So there's a trade-off between how many iterations you use and what's an acceptable delay or performance penalty to pay on your website. So typically, I've used 100,000 iterations or sort of thereabouts before, which is about a 1.5 second delay when someone logs into a website. The company I was working for at the time, we deemed that acceptable. But if you ever log onto a site and there is a slight pause, it's probably because they're doing a password-based key derivation function behind the scenes. So does anyone remember or know what this website is? Ashley Madison. So their best way to describe them is a dating website in the US, but it's a dating website for people that want to have affairs. So not a particularly nice website, but they got hacked a few years ago, and they had all of their passwords stolen. Now, what was good in terms of them is they were using something called bcrypt to hash their passwords. Now, bcrypt is exactly, well, it's the same principle as a password-based key derivation function. It's just a different algorithm, but the concepts are the same. It's a password, a salt, and a number of iterations. So they were using that to protect their passwords. That's great. But one enterprising engineer at the company thought he'd try and optimize the system so that when a user logged onto the website, it would create a local token with an MD5 hash of the password in, so that next time you log in, it would be faster. So when the hackers found this out, because they stole the source code to the site as well, they then used that as a basis of a new attack, where they attacked the MD5 codes instead of the stronger hashed passwords, which meant they could recover 11 million passwords. So there's an interesting article about it here on Ars Technica, which goes into more detail about how they did that. But the reason I'm talking about it now is it proves that your security is only as good as the weakest link in your system. So whilst they did have a good password storage mechanism, one of their programmers compromised it by putting a weak link into the system, and that's what the attackers went for, and they got 11 million passwords out of it. Okay, so the next bit then is symmetric encryption. So we're getting onto some of the good stuff now. So symmetric encryption is where you use the same key to both encrypt and decrypt your data. That's why it's called symmetric. So you have some plain text information. That could be a PDF file, an image, or any data in your system. You encrypt it with a known key, or known to you. That produces the ciphertext, and then to turn the ciphertext back into the original document, you use the same key to decrypt it. That's all well and good, but sharing these keys is very hard. So if I encrypt some data and I want one of you to be able to decrypt it, how do I get that key to you? So do I send it over email? Probably not a good idea. Do I put it on a USB key? Again, probably not a good idea. And every mechanism you try and think of how to exchange that key, you can think of about 10 different ways it can be compromised. So really the best way for me to give you that key is probably just to give it to you in person, which isn't practical over the internet. So again, just sort of illustrating the point then that encryption is a two-way operation. Encrypted data can be decrypted, whereas what we discussed before with hashing is a one-way operation. Now, the way symmetric encryption works is it will encrypt several bytes at a time, and these bytes are formed into blocks. So even if you have really huge files, it's actually relatively fast to encrypt that data, because it's all split into blocks, and each block is encrypted with the next block, and so on and so forth. And the blocks are all padded so that they're the same size. So when you get to the end of a file, that last file is padded out, so it's the same size as the previous block. There's various different ways of doing symmetric encryption in .NET. So we have DES and triple DES, which are older encryption algorithms. So generally you wouldn't use those, or you shouldn't use those for new systems. But again, you might be working with legacy systems where they are using DES or triple DES. I worked for a bank once, and we had our core platform was an old IBM AS400 mainframe, and data in that was encrypted with triple DES. So as we pulled data back into our sort of nice brand new .NET stack, we had to decrypt it with triple DES. But if you're creating a new system, then AES, or the Advanced Encryption Standard, is the system you want to use. So AES it became a standard in 2001 in the United States National Institute of Standards and Technology. And it was invented by two mathematicians, so Joan Damon and Vincent Ryman, and it was based on an encryption algorithm called the Ryman cipher. And the way this works is quite straightforward. So AES requires several things to make it work. So we need our plain text data, which we want to pass in, so that's a message we want to encrypt. It requires what's called an initialization vector, and what that is, it's 16 bytes of random data, and that's used to effectively jumpstart the encryption algorithm. The initialization vector doesn't need to be secret. You can store it in your database along with your data. And then we pass in an encryption key, which can be 128, 192, or 256 bits in length. So we're going to use 256 bits. We'll just go straight for the stronger key. So you pass all of those into AES, and then you get your encrypted ciphertext back out the other end. Now in .NET, there's two implementations of AES. There's AES Managed, and there's AES Crypto Service Provider, and they both do the same job. But AES Managed is written in .NET, well, written in IL, so it's native .NET, and it's fine, it works very well, but it's not certified. So there's a certification called FIPS 197-2, and what it means to be certified is if, say, for example, you encrypt something in .NET, and then you've got a Ruby implementation, which is also FIPS certified, you can guarantee that that Ruby implementation will be able to decrypt that data. So AES Manage isn't certified, so there's no guarantee that another system will be able to decrypt that data because it's not been tested. Although I've never seen any instances where it can't be decrypted, but it's not certified. But AES Crypto Service Provider, on the other hand, is FIPS certified. And that's not written in .NET or C#. It uses the underlying crypto platform in Windows. So it's a little bit more involved. I hope people can read that at the back. But again, it's still fairly simple to encrypt some data. And the sample code you can get off my GitHub has all of this in, so feel free to steal it if you want. But into the encrypt method, we pass in a byte array of our data. We pass in the byte array of our key, which is going to be 32 bytes. And we pass in a byte array of our initialization vector, which is just a 16-byte random number. We create an instance of the crypto service provider. We pass in the key and the initialization vector. And we then create a memory stream and a crypto stream. And then we write the data into that stream. Once it's finished, you say memory stream.toArray, and you get a byte array back with a load of data, with your encrypted data in it. Decrypting the data is virtually the same. So the only difference is on the line where we create the crypto stream, it passes in AES.createDecryptor instead of createEncryptor. So it's virtually identical in how it works. Okay, so the next encryption algorithm we're going to look at is asymmetric encryption. And this is what you'll commonly known as public and private key encryption. And the one we're going to look at today is RSA. So the way this works is you have some data that you want to encrypt, and you get the public key of your recipient, and you use that to encrypt the data. So it's your recipient's public key, but it's public. Anyone can know it. They can email it to you. You can download it off the internet. It's not secret. So you encrypt with the public key. You then send them the result, and then they use their private key, which is only known to them, so they don't share this. They keep it safe, and then they can decrypt that data. So it's a good way of being able to use encryption without having to pass keys between people, or secret keys between people. So RSA was developed by RSA Data Security Incorporated by three guys called Rivesh, Shamir, and Edelman. And whereas AES is very algorithmic in how it works, it splits data into chunks or blocks, and it encrypts those blocks. The way RSA works, it's all based on modulus arithmetic and prime numbers. So current minimum key length which you should use is 2048 bits. You can go higher, but you suffer a performance penalty if you do that. One of the pitfalls or one of the problems with RSA is that you're limited to how much data you can encrypt in one go. So generally you're limited up to the length of the key, which is 2048 bits. So you can't encrypt more than that, just due to how the mathematics works. So what you could do is you could take a large piece of data and split it down into smaller chunks and encrypt each one separately. That would work, but it would be quite slow. So RSA is very slow. So the way RSA works is it's based around prime number factorizations. So if I was to say to you, get the two prime numbers, 23 and 17, and multiply them together, it's quite easy to work out what the answer is. It's 391. But if I was to say to you, what two prime numbers do you multiply together to make 5,963? Does anyone know the answer? So the answer is 67 and 89. So that's kind of how, as a rough, broad principle, how this works. So the fact that it's difficult to work out the prime numbers that you use to generate a larger prime number is where the security for RSA comes in. So if we map this back to public and private keys, so in this case our public key is 5,963, and the private key is 67 and 89. So those are the numbers we don't want people to know. Now obviously that's a very simple, trivial example. The actual length of these keys is massive. They're like, 2048 bits is a very large number. And the idea is that machines can't process or work out the primes for that large number. Not at the moment, anyway. So to use it, it's quite straightforward. So first of all, we want to generate our key pairs. So we create a class, or an instance of a class called RSA Crypto Service Provider, and we tell it what key length we want. And then we call export parameters passing in false, and that gives us our public key. And then we call the same again, but passing true, and it gives us our private key. So in this example, we're just storing them in two member variables. Then to encrypt our data, so we just pass in the data we want to encrypt as a byte array. We create the RSA Crypto Service Provider. We import our public key, and then we call the encrypt method, and that gives us a byte array back out the other end. And similarly, to decrypt that data, we pass in our encrypted data, we import the private key, and then we call rsa.decrypt. So, complex principles, but actually the implementation is quite easy to use. Okay, so the final primitive I want to look at before we get onto hybrid encryption or hybrid cryptography is digital signatures. And these kind of build on the principles that we've just looked at for RSA. So with digital signatures, we've got three different algorithms that we want to use, or three different things we want to be able to achieve. So first of all, we need to be able to generate keys. Well, we've just looked at how to do that with RSA. It's exactly the same. And then we want an algorithm that we use to sign some data. And then we want an algorithm which can verify that a signature is valid. So the way you generally do this then, so you have a large bit of data, and typically that's going to be bigger than 2048 bits. It could be a very large PDF document or an image or some other data in your database. So then we create a SHA-256 hash, or HMAC of that data. So that gives us a 32-byte hash code. And then we sign that hash code. That's what we create a digital signature of. So if we look at an example with my brilliant coder art, I do apologise, I'm not very artistic. So here we have Bob, and he wants to send some data that's been digitally signed to Alice at the bottom. So what Bob does is he creates a digital signature, but he uses his private key. So if you remember back to when we used RSA, when we encrypted the data, we used a recipient's public key to encrypt the data. But to generate a digital signature, you use your own private key to generate that signature, so it's only you that knows that key. So once he's done that, he sends the data over the internet, or the big spider's web, as I've drawn it there. And then Alice uses Bob's public key to verify that that signature is valid. So the reason why this is important is that Alice now can be sure that it was definitely Bob that sent that information to her, because only Bob could have created that signature using his private key. And then Alice has verified that signature using Bob's public key. So she knows for sure that it's definitely come from Bob. So to use it, it's straightforward. So first of all, we need two keys, a public and a private key. So this is the same code as what we saw before. And then to create a digital signature, we need to use a class called RSA PKCS1 signature formatter. Again, I'd love to meet the person that named that class, because it's not very obvious what it does. But we create the RSA object, we import our private key, because we're creating a signature with our private key. We create the signature formatter class. We set the hashing algorithm to SHA-256, because that's what we've used to generate the hash. And then we pass in the byte array of the hash code that we want to sign, and then we just call create signature. And that gives us a byte array back, which is our digital signature. Then to verify that that signature is valid, we again create the RSA crypto service provider. We import the sender's public key this time. And then we create an instance of RSA PKCS1 signature deformatter. There's a pattern form in there. And then we call verify signature, and we pass in the original hash code, which is the original digital signature, or the original hash code that we generated the signature for, and we pass in the signature. If it's valid, it returns true. If it's invalid, it returns false. So what does that mean? So true means that we are confident that the person who sent us that digital signature is valid. We know it's definitely come from Bob. If it's false, then that means that the digital signature doesn't match that piece of data with that key. So in that case, we shouldn't trust the digital signature that's been sent to us. Okay, so if we recap on the 4 pillars of cryptography that we talked about before. So we've got confidentiality, and to get confidentiality, we've discussed AES and RSA. Then we've got integrity, which is about creating hash codes, and we've used SHA-256 as our primitive for that. And then for authentication, we've discussed HMACs using SHA-256. And then for non-repudiation, proving that someone is the correct sender of a piece of data, we've used digital signatures. So now what we want to do is to use all of these things together to create something more powerful. And this is called hybrid encryption. So what we've discussed already then, RSA has limits on the amount of data you can encrypt in one go. So you're limited by sort of the length of the key. But with RSA, we want the flexibility and the speed of RSA, because it's very fast at encrypting data, it's very algorithmic, but exchanging the keys is very hard. So what we want to do is combine the two together to give us a fast, efficient encryption mechanism where it's easy to share the keys. So the way this works then is we generate an AES key, and we call it the session key. So that's 32 bytes of data. We then encrypt our data using that key, just as we have done previously. Then what we do is we get the recipient's public key, and we encrypt that session key. And then we send that encrypted text and that encrypted session key to our recipient. Then once they've received that message, they use their private key to decrypt the session key, and then once they've recovered that key, they can then decrypt the original message using AES. So if we work through that as an example, so the packet of data that we send across the network, this is what it looks like. So we've got the RSA encrypted session key. We have an initialization vector, because remember we need that to get AES going, and we have our encrypted data. So that's what we've sent to the recipient. So if we work through that as an example, so Alice generates her session key, that's 32 bytes. She then generates an initialization vector, so that's 16 bytes of random data. She then encrypts her message with AES. And then using RSA, she uses Bob, because Bob's a recipient, she uses his public key to encrypt that session key, that AES session key. And then she sends a whole lot over to Bob. So on the other end, Bob uses RSA in his private key to decrypt that session key. So he's now recovered that AES key. And now he's got that key, and he's got the initialization vector already, he can decrypt the original message. So the message he's got is, meet me at noon below the clock tower, wear a rose in your button. Very, very James Bond. So now Bob wants to send a reply back to Alice. So he's going to do exactly the same, but the other way. So he generates a new session key, because you never reuse the same keys, you always generate new ones. And he generates a new initialization vector. Then Bob encrypts his data using that session key. So he's encrypted his response. He then encrypts that session key with Alice's public key. So it's the public key of the recipient of who he's sending the data to. And he then sends that over to Alice. So she's now received that data, and she uses her private key to recover that session key. And then using that session key and the initialization vector, she can decrypt the message with AES. So the message is, I will meet you, I'll be wearing a blue hat and red boots, because Bob's clearly got very good fashion sense. So let's take that a step further. So we've shown how we can use RSA and AES together to send a message, but not have to share keys directly. But now we want to make sure that the integrity of the message is intact that we send to the recipient. So we want to make sure that it's not been corrupted in transit, or anyone's intercepted that message and tampered with it. So what we do is we extend on what we've just built. And once we've encrypted the ciphertext with our session key, we then create a hash map, or an authenticated message code, of the ciphertext and initialization vector combined. And that hash map is calculated using that session key that we just generated. So the only way that the recipient can regenerate that hash code is if they've recovered that key. So if we look at the data that we send to our recipient, so we've got the RSA encrypted session key, same as before. We've got the initialization vector and the encrypted data. But we've also got another hash, an authenticated hash that we're sending as well. So that means that the recipient has to be able to recover the session key with their RSA private key before they can regenerate that hash. And then once they've done that, they can actually check that the message is intact, because the hash code should match when they recalculate it. So extending on that a little bit more then, so we now want to be able to prove to Alice that it was Bob that actually sent that message. So this is where we're going to start incorporating a digital signature. So we're going to do everything that we've done before. So RSA to protect our session key, AES to encrypt our data, a hash map to create a hash code of the encrypted data. But now the sender is going to sign that data with his private key. So if Alice is sending a message to Bob, she uses her private key to generate a digital signature of that authenticated hash. So that when the message goes across to Bob, he has to use Alice's public key to verify that digital signature is valid. So you can see how we've used all those primitives and we've built them up on top of each other to give us all four of those pillars that we discussed before. So we've got confidentiality, because we've encrypted the data. We've got integrity, because we've got the hash map around the data, so we know if it's been tampered with. And we've got authentication, because we used a key with our hash algorithm. And we've got non-repudiation, because we've generated a digital signature with the sender's private key. So this means that we can prove that it was the sender that sent that message. So again, if we look at the data that gets sent across, exactly the same as before, except at the end we've got a digital signature of that hash map code. Okay, so that's quite a lot that we've covered there. So has anyone's brain melted yet? No? Oh, cool. So it is quite a lot to cover in one go. So I think the best way to treat this, this session is it's kind of an art of the possible. So I wouldn't expect you to remember every single bit of it straight after the session, which is why, as I said before, I've got various different resources available to you. So if you do want to explore this in more detail, you can watch my Pluralsight course. It's a 4-hour course. It goes into a lot more detail about why you do a lot of these things. If you haven't got access to Pluralsight and you want to watch it, if you go to my blog, which I'll show you the address at the end, you can contact me and I can send you a code to give you 30 days unlimited access to Pluralsight. So you can watch this and everything else that's on there. Okay, my most recent course is this one here, which is about using Azure Key Vault. So the example I use in this course is the hybrid encryption example, but I'm storing the encryption keys in the Azure Key Vault. So it means it's all being backed by proper hardware in Microsoft. And this is quite important because obviously key management is important. You don't want your private keys to get compromised and lost. So Azure Key Vault is a way of protecting those keys. And they're using proper industrial hardware security modules behind the scenes to do that for you. So as an example, I said I work on a product which is for the insurance industry, but that means we store lots of insurance data in Azure. Oops. We store lots of insurance data in Azure. So one of the things that they're very keen about is how are we encrypting the data, and has each insurance company got their own sets of private keys, which they have, and they're all stored in Azure Key Vault. So this course talks you through how to build that. If you go to my GitHub repo, I've got all the sample code from that first Pluralsight course available. So you can just download it, everything builds, and you can just use whatever in there. You can use the whole lot. And also my slides are on GitHub as well. So if you want a copy of these slides, just go to that address, and they're up there for you to refer to later. Got some other books here. So these are 3 books which I highly recommend. I personally think cryptography is a fascinating subject. I might be in a minority there, I don't know, but the fact you've all turned up to see this session kind of tells me that you're probably interested in it as well. So the first book is called The Code Book by a guy called Simon Singh. This is quite an entertaining read. It's about the history of cryptography and encryption. So it goes back to like Mary Queen of Scots and all the ancient times and how they used to send messages to people. The book's about the size of a novel, so it's quite an easy read. I even read it on holiday once to my wife's dismay. The next book is called Everyday Cryptography, and this is a fantastic book. So the first half of the book talks about how these encryption algorithms work that we've discussed today. So it goes into quite a lot of deep maths. But then the second half of the book talks about how that's applied to everyday things. So, you know, when you put your PIN code into a cash machine, how does that handshake between the bank work? You know, how does the handshake between 2 machines, when you do a TLS connection, how does that work? So it puts a lot of this into practical context. It's a very good book. And probably the most famous book, and is one that the NSA tried to ban originally back in the early 90s, is a book called Applied Cryptography. So it's quite an old book, so it doesn't cover AES, but it does cover things like DES, triple DES, blowfish, and a lot of the other ciphers that are out there. So if you want to get a good view on how a lot of these algorithms work, it's a really good book to refer to. But it is a very thick book. It's about that thick, so it's not for the faint of heart. So thank you very much. Thanks for coming along. I hope you've enjoyed it.